Hi all. Today we're going to learn about topic 8. So this is a three-part lesson. The first part we're going to deal with looking at electronegativity and polar bonds, and that's going to make up this video. And then in other lessons we're going to go and look at polar molecules and then see how we can use polar molecules to understand what the intermolecular forces between molecules. Okay, so our learning goals for today are to explain the difference between nonpolar and polar covalent bonds, define electronegativity. We're going to try to calculate the electronegativity difference between atoms and use that to classify the bonds as nonpolar covalent, polar covalent, or ionic. And we're going to explain the characteristics of each bond type. So we've learned that in a covalent bond, we have two electrons or more that are being shared between two elements. And they're sharing to get a full octet to get a noble gas-like arrangement. And we've been working on the assumption that when we have those covalent bonds, they're actually being shared equally between the two elements. But we're going to learn that's not always the case. Sometimes one element will have a greater pull on those electrons than another, resulting in changes in terms of the characteristics of that bond. And that's really what we're going to be looking at today. So in a nonpolar covalent bond, the electrons in that covalent bond are being shared equally. Okay, and that results in no charge buildup in that bond. So if we look at, for example, the example that we have here, we have chlorine, right? We can see here that we have Cl and Cl. Okay, we have our lone pairs around it, and then we have our bonding electrons. In here, because chlorine is the exact same element, it has the same pull on the electrons. So they're going to be shared equally between these two elements. So those electrons are going to be basically right in between both of those Cl's, resulting in no charge buildup. And we'll see nonpolar covalent bonds occur when we have elements that have similar electronegativities. Okay, and in this case, we're dealing with chlorine, a bond with chlorine and chlorine. They have the exact same electronegativities, so they have the same pull on the electrons and no charge buildup. If we remember, electronegativity is defined as the ability of an atom to attract bonding electrons. We can think of that as a tug of war. So if we have two people that have the similar strengths and they do a tug of war, that rope over here is not going to move and it's going to stay at the same place. And that's exactly what we saw with when chlorine was bonding with itself, right? It was having a tug of war for those bonding electrons, and each one pulled it equally, so the electrons were shared equally between. But if we have an element that has a stronger pull on those electrons, as an example here, oxygen and hydrogen, in that case, one of them will have a greater pull, and that's going to pull the electrons closer to one of those elements. And that's going to change the properties of that bond. And we'll see what that means in a moment. So we can find the electronegativities for all elements on the periodic table, okay, using the table that you guys have. Okay, so if we look at our table here, you're going to see in our legend, you'll see here that there's a spot here that says electronegativity, and we have a value written down. So we can look anywhere on the periodic table. So if we're looking at nitrogen, the electronegativity for nitrogen is 3.0. If we're looking at arsenic, it is 2.0. If we're looking at cobalt, it is 1.8. Okay, so we're going to see how we're going to use this. So I do recommend that you do take out your periodic tables as we go through this lesson. Okay, so a polar covalent bond happens when the electrons are not being shared equally between the elements involved. Okay, and that'll result in a charge buildup within that bond. So when you have a charge buildup, you're going to have one side that is slightly positive and the other one that is slightly negative. Okay, and this happens because the elements that are involved have different electronegativities. Okay, and we're going to see a little more about that in a minute. So in this case, if we look at these two elements, okay, if we look at chlorine, okay, and you look on the periodic table, you're going to see that chlorine has an electronegativity of 3.0. Okay, and if we look at hydrogen, it has an electronegativity of 2.1. Okay, so chlorine has a much higher electronegativity, which means it has a stronger pull on those electrons. Okay, if it has a stronger pull on those electrons, the electrons are going to be spending more time closer to chlorine than they will to hydrogen. And because electrons are negatively charged, if those electrons are spending more time closer to chlorine, then chlorine is going to be slightly negatively charged, okay? And the hydrogen is going to be slightly positively charged. Okay, and we can see this notation here where we have this, what looks like an S closed off, so slightly negative and slightly positive. And that's the symbol that we're going to use to represent that. Okay, so when we have elements with different electronegativities, the one that has the higher electronegativity is going to have a greater pull on those electrons, which means it's going to be spending more time closer to that element, and it's going to make it slightly negative, and the other element is going to be slightly positive. So in here, if we're looking at the notation, okay, so this symbol that we talked about here represents slightly negative, and that means that the bonding electrons are spending more time closer to that element. Over here, we can see that the slightly negative, or the slightly positive, sorry, means that the bonding electrons spend less time closer to that atom. We can determine who's going to be positive and negative based on the electronegativity. The more electronegative atom is going to be the one that's negative because it has a greater pull on those electrons, and the one that is less electronegative is going to be the one that's going to become positive. Okay, so how can we predict if there's going to be a charge buildup in a bond? We're going to compare the electronegativities between the two atoms. Okay, so we're going to calculate the delta N, and we're going to subtract the most electronegative element from the least electronegative element. Okay, and the bigger the difference, the more charge buildup or the more polar that bond is going to be. Okay, when we're calculating delta N, it will always be a positive value because we're always taking the largest number, subtracting it from the smallest. Okay, so if we look at the example that we did there, we solved for the difference in electronegativity between chlorine and hydrogen. So we had 3.0 minus 2.1, and we got 0.9. Okay, chlorine is more electronegative than hydrogen, so the bonding electrons will spend more time near chlorine, and hydrogen will be slightly positive. Okay, so in here we have a first sample problem. It says determine whether there will be a charge buildup in the following bonds. If there is a charge buildup, identify the partially positive and negative atom. Okay, so what we're going to do is we're going to go look on the periodic table. Okay, so if we look up oxygen, we're going to see that its electronegativity is 3.5. Okay, if we look up hydrogen, we're going to see it's 2.1. Okay, so we're going to calculate our difference in electronegativity, and we're going to have 3.5 minus 2.1, and we get a value of 1.4. Okay, so in here, because we have a differential that we see, there will be, let me just see if I can click here. Therefore, there will be a charge buildup. Okay, if we look at here, oxygen is going to be slightly negative and hydrogen is going to be slightly positive. Oxygen slightly negative because it has a higher electronegativity. Hydrogen is going to be slightly positive because it has a lower electronegativity. Okay, so now if we look at our next example, see if you can pause the video and try it on your own. Okay. If you look at phosphorus, it has an electronegativity of 2.1. Hydrogen has one of 2.1. If we do our delta En, we get 2.1 minus 2.1, which is 0. So therefore, no charge buildup. Okay, and we won't indicate any charges there because there is no charge buildup in this bond. Okay, so when we're classifying bonds, the absolute value of the electronegativity difference of the two bonded elements will give us a measure of the polarity. Okay, if we have a difference in electronegativity between the two elements and we get a value that is less than 0.5, the bond is classified as a non-polar covalent bond. Okay, if we get a difference in electronegativity between 0.5 and 1.7, it will be classified as a polar covalent bond. If we get a difference in electronegativity of greater than 1.7, we're going to classify it as an ionic bond. Okay, the greater the difference in electronegativity that we get, the more polar and then the more ionic the bond becomes. So the bigger the number, the more charge buildup that we're going to have. Okay. When we're looking at a nonpolar bond, the electrons are being shared equally. In a polar covalent bond, one has a greater pull, but they're still being shared between the two elements, making one side slightly negative and the other side slightly positive. It's slightly because those electrons are still being shared. But once you get over 1.7, one element is so strong and so able to pull those electrons that it completely rips it away from the other element, resulting in a full positive and a full negative. So we can really look at this as a continuum, okay, where we're using these cutoffs to classify them, okay? So in here, if we're between 0 and 0.5, we're classified as nonpolar. If we're between 0.5 and 1.7, we're classified as polar. And if we're greater than 1.7, it's classified as ionic, right? But if we're right on the cutoff, so let's say we had a value of 0.5, okay? If you got a delta N of 0.5, that would be classified as a polar covalent bond because it's between 0.5 and 1.7. And we would say there's a charge buildup. But the charge buildup that you have would be a lot less than something that has a delta N of 1.5. Okay, so this is a continuum. If you have something with a delta N of 0.45, it would be classified as a nonpolar bond. Okay, but it would still have a little bit of a charge buildup. But for classification purposes, we would say that it has no charge buildup. Okay, so this is a continuum that increases as we go from left to right. Right, and we're using very harsh cutoffs to classify these bonds. Okay, but whenever we're around kind of the edges, okay, we're going to see that it does have a little bit of properties of both, and that's okay. And we're going to find also when we're classifying the bonds, it may not match with how we classify the molecule. So we might classify the bond as ionic, but the molecule is covalent and vice versa. Okay, and it's just based on the way we're defining these. For defining molecules, we're using metal, nonmetal. For classifying bonds, we're using our differential in electronegativity. Okay, so you guys have this chart. See if you can fill it in. Okay, so if we look at this now, when we're looking at covalent bonds, okay, we're really saying that they can be broken down into two different types. One is a nonpolar covalent bond, and one is a polar covalent bond. Okay, in a nonpolar bond, the electrons are shared equally. Polar covalent bond, they're not. And then we get into an ionic bond, and there is a full electron transfer. Okay, so we have one more sample problem. So in here, it's asking us to classify the bonds as nonpolar covalent, polar covalent, and ionic. And I'll add an extension to that to indicate any charge buildup that happens. Okay, so to do this, we're going to go look up on the periodic table for the electronegativities. So if we go and we look at calcium, we have 1.0. If we look at chlorine, that is 3.0. So we're going to calculate our delta En, and we have 3.0 minus 1.0, and we get 2. So therefore, this bond is going to be classified as an ionic bond because delta En is greater than 1.7. Okay, and in here, because this is classified as an ionic bond, chlorine is going to be fully negative and calcium is going to be fully positive. Okay. So if we look at B, I would recommend pausing it and trying this on your own and then seeing the full solution. So if we look at nitrogen, it has an electronegativity of 3.0. If we're looking at oxygen, it is 3.5. So we're going to calculate our delta En. And we have 3.5 minus 3.0, and we get 0.5. So therefore, this is a polar covalent bond because delta En is between 0.5 and 1.7. So if we have a polar covalent bond, the electrons are going to be shared unequally, and the one that has a higher electronegativity is going to be slightly negative, and the one that has a lower electronegativity is going to be slightly positive. Sorry, bear with me a second. All right, last one. So here we're looking at carbon. So we have 2.5. Sulfur is 2.5. We do our delta En. We get 2.5 minus 2.5, and we get 0. So this is going to be classified as a non-polar covalent bond because our delta En is less than 0.5. Okay, those cutoffs you will have to memorize. There's really no way around it, but you'll find it's not too bad because we really only need to know those two numbers. Okay, so that basically takes us to what I wanted to cover. Okay, so we're now looking at trying to further understand the bonds that happen. If we look at covalent bonds, we can have two types, right? We can have a non-polar covalent bond where the electrons are shared equally. We can have a polar covalent bond where the electrons are shared unequally, and that's because one of the elements have a higher electronegativity and a greater pull on the electrons, making one slightly negative and slightly positive. In an ionic bond, we still have a full electron transfer that happens. That's because there's such a big electronegativity difference that one element can completely take that electron away. Right. If you have any questions, let me know. There is going to be some homework for you to do, and it will be posted on ANSPI.